Hello everyone, and welcome to the Apache Avro in Practice talk. In this talk, we will go over the core functionality of Apache Avro and some of the practices that I leverage in my projects. First, let me introduce myself. My name is Zoltan Farkas. I started programming in BASIC on a Sinclair ZX Spectrum. I graduated the Polytechnic University of Timișoara in Romania. My engineering career is spanning telecommunications and finance. As a consequence of using Apache Avro in my projects, I eventually became an Apache Avro contributor. You can see some of my contributions referenced here on this slide, along with my GitHub information, where you can find some of my other open source work as well. Here's the obligatory disclaimer. The content and opinions in this presentation are my own. So let's start with an overview of Apache Avro and some of the main reasons one would choose it over other serialization frameworks. First, dynamic typing. Avro does not require that code be generated. Data is always accompanied by schema that permits full processing of that data without code generation, static data types, etc. This facilitates implementation of generic data processing systems and languages. Second, Avro does not have manually assigned field IDs. No type information is serialized, resulting in a more compact binary representation. Avro also supports multiple encodings. Binary and JSON are supported out of the box. Other encodings are possible as well, and available via third-party libraries like XJSON or CSV. Avro also supports compatible schema evolution. You can add, remove, rename symbols or fields while keeping your model convertible to and from previous versions. The Apache Avro project supports multiple languages like Java, JavaScript, Python, C, C++, C#, Perl, Ruby, and PHP. This allows components written in different languages to seamlessly interoperate using the Apache Avro framework. Avro comes with a rich, extensible schema language defined in pure JSON. This is how Avro schemas are serialized and shared between systems. The choice of using a JSON format provides a good compromise between machine and human consumability. In this slide, you can see an example record definition for a character entity with a few fields of type string. You can build a lot more complex data models leveraging Avro's rich type system. Avro's type system covers primitives like null, boolean, int, long, float, double byte, string, and complex types like records, enums, arrays, maps, unions, and fixed. There is also a higher level language available for authoring Avro schemata via Avro IDL. The Avro IDL schema definition can be converted to and from the JSON representation. On this slide, we can see the same schema from the previous slide in a more human-readable form. Less curly braces, less double quotes, less escape sequences result in a schema that is a lot easier to read and comprehend and write as well. If you're building generic data processing tools and systems, the Schema Builder API is available for you. In this example, you can see the same schema from previous slides being built in the Java language. As mentioned before, the schema objects built this way can be easily serialized and deserialized into their JSON representation. One can easily create a schema dynamically, as shown here, and read and write data that complies with it. On top of a rich type system, Apache Avro supports the concept of logical types. Logical types facilitate improved type safety by extending the core types. Avro does not have first-class type support for decimal or date. However, the logical type concept allows you to implement them on top of the existing types. On this slide, you can see two examples of logical type implementations included with the Apache Avro library. In the first example, you can see how you can use the decimal logical type, which is implemented on top of the bytes Avro type. And in the second example, you can see how you can use the date logical type built on top of the integer type. For information on complete logical type support in the Apache Avro library, see the URL referenced in this page. Logical types is something that users can create themselves for their own specific need. And, and as you can see in this example, some of the logical types I have implemented, like support for URL logical type on top of string, or the any Avro logical type on top of record, and the JSON record logical type on top of string. The implementation of these logical types with examples you can find in the Avro repository on my GitHub space. One of the other nice features of Apache Avro specification is that it allows you to add your own metadata to your schema. In this slide, you can see highlighted how we can add record metadata and field level metadata to both your JSON and Avro IDL representation. You can see attribute 1 added as metadata for the character record and attribute 2 added for the name field. Seeing the two representations side by side makes it obvious why AVDL is my preferred format for schema specification. In the previous slide, we have seen how easy it is to add custom metadata to your schemas. On this slide, you can see two of my favorite custom metadata attributes. First, the beta attribute, which informs the user and the compatibility validator that no compatibility guarantees will be made for this type. This is very useful in the beginning phases of a project, where you don't want to be constrained by the compatibility validator for no good reason. Second, the deprecated attribute, which informs the user that this schema type or field is deprecated, and that it will be removed in the future. The compatibility validator can also make sure that you will remove this field according to your deprecation policies. Additionally, your system can log access to the deprecated data fields, helping you in the operational aspects of deprecating data. Deprecating and removing fields is a very difficult and it is a complex process. So you want your system to help you as much as possible in that process. Apache Avro also comes with a container file format. This comes in handy every time you need to persist your data to a file system. And it is my favorite format for storing logs, metrics, profiles, and basically any other data. Having your data in Avro files makes your data easily accessible in Apache Spark, Hive, etc. The Avro file starts with the header. The header contains the schema of the data contained in this file, the compression type, and the user metadata. The user metadata you can use to store data lineage information or anything else that you might find useful. After the header, the data content follows in either JSON or binary encoding, compressed with the chosen compression algorithm. This concludes the Apache Avro overview part of my presentation. We did not cover everything that Apache Avro offers, like Avro RPC, but I hope everyone has a general idea about the core functionality of the Apache Avro serialization framework. After deciding to use Apache Avro in your projects or any other serialization framework for that matter, the first thing one should come up with and implement is a data model lifecycle. Here are some of the goals one should have. First, compatible schema evolution. In any non-trivial application, you will need the ability to evolve your schema in a compatible way. This will enable you to make changes to your components independently. Second, you will want to have a process, both automatic and manual, to ensure the quality of your data models. You will also want to be able to share and reuse your data models. Developers should be able to easily discover and understand your data models and create new ones without copy and paste. When creating your data models, you will also want to be able to seamlessly collaborate. In the next slides, we will go over one approach we can use to achieve these goals. The first thing we will probably look into is where to put our schemas. And a version control system like Git with a change management workflow like pull requests will fit the bill nicely. On this slide, you can see a screenshot of a schema project that I published on GitHub. This way, I can collaborate with anyone with a GitHub account and evolve my data model. Next, to solve versioning, dependency management, validation, code generation, and publishing, we can use Apache Maven. If you're familiar with Apache Maven, in this slide you will recognize the phases in a Maven project lifecycle and how we apply them to build and deploy, release our schemas. In the initialize phase, we retrieve this module schema dependencies from the Maven repository and unpack them for import. In the generate sources phase, we generate the language object source code. You can do that for multiple languages. In my example from the previous slide, I only published the Java generated code. However, we have done the same for C# and TypeScript in past projects with Maven. In the compile phase, we compile the generated sources. In the process classes phase, we generate the documentation for our data model. In the test phase, we run our compatible evolution checks and verify compatibility with the previously released versions. We will also run other quality checks like naming conventions, documentation quality checks, etc. You can write your own custom checks. In the package phase, we generate the schema package, which is basically a zip file containing all schema JSONs plus an index file. In this phase, we also generate other packages like the jar file, sources, Java doc package, etc. In the install phase, we will publish the packages to our local Maven repository. And in our deploy phase, we will publish them to our remote repository. And that way we will make them available to everybody else. The heavy lifting like compatibility validations and quality checks is being done by the SPF4J Maven Avro Schema plugin, while the documentation is generated with the AvroDoc utility. Both are open source and available on GitHub and Maven Central for the Maven plugin and NPM in case of AvroDoc. AvroDoc is written in JavaScript and published to NPM. When using Maven, the root folder of the schema module will have a pom.xml. This is where we will declare component identification, description, and dependencies. Your component will be identified by the Maven group ID, the artifact ID, and version. You can see these highlighted in the example POM file on this slide. Maven also comes with a standard project layout, which makes each schema component uniform and easy to understand. So you will find the schema definition at the same location in every single schema project that you will look at. The schema definitions will be placed in SRC main Avro. You can use either Avro IDL or JSON format to define your schemas. I prefer the Avro IDL since it is a lot easier to read and write. When deploying a Maven schema project, a collection of packages will be deployed to your Maven repository and documentation published to your GitHub Pages branch or Maven site. In this slide, you can see the results of the core schema project, where we publish our schemas to Maven Central and make them available basically to the entire world, along with the Avro documentation published to its GitHub page. The packages that we publish in this example are the Avro schemas, the Java jar file, the Avro doc documentation, the Avro sources, the Java sources, and the Java doc. You can see on this slide also a screenshot of the published Avro doc, the generated Avro documentation. To recap the previous few slides, Git and Maven enable us to implement a source repo to schema repo workflow. Here is what the process looks like. To implement a new schema or a schema change, a developer will create a branch with his changes, push the changes to the main Git repo, and then create a pull request. On pull requests, MVN test will be executed automatically and will validate compatibility and quality of your changes. If everything looks good, next a peer will validate the changes from a human perspective and request modifications from the author if needed. If everything looks good, the changes are merged into the master branch. This will kick in a publish of the changes to the Maven repository and make them available for everyone to use. As you can see, the process is similar with the typical process of developing a Java library. We have seen how schemas can be published to Maven repositories. Now let's see how we can reference individual schemas, like, for example, the method record schema from the core schema package that we used as an example in my previous slides. We will need to create an identifier that uniquely identifies a specific version of this Avro schema. To uniquely identify a particular schema, we can use a tuple containing the Maven group ID, the artifact ID, the version, and an identifier that uniquely identifies the schema within the module. In the example on this slide, org spf48.avro core schema 101:2 would uniquely identify a version of the method record. The mapping from 2 to the fully qualified name of the method type is contained in the schema index.properties file located in the package. The reason why we have this mapping is to shorten the identifier size. A 2 is obviously a lot shorter than the 10 plus characters that we use for the fully qualified names usually. With an identifier like the one defined in the previous slide, we can implement an Avro schema reference as shown in the example on this slide. The official Avro distribution does not implement the concept of references. However, we can implement them by introducing a custom attribute. As shown in this example, we can use a ref attribute that will have as a value the Maven's key identifier, which I explained in the previous slide. A JSON preprocessor will resolve these references by querying Maven for every ref attribute it finds and replace them with the schemas resolved from the Maven repository. In this example, the ref field is resolved into into a record schema. You can also clearly see the role references have in reducing the schema size. This makes it feasible to use Avro schemas in protocol headers like HTTP or other messaging protocols. Here is a slightly more complex example of a schema with an array of records this time. As you can see, Avro references can be anywhere in an Avro schema, and you can have multiple references as well. As seen in the previous slides, references make type information being sent in protocol headers feasible. But they still need to be resolved by the data consumers, and that comes at a cost. Since release schemas are immutable, they can be cached forever. A process that will resolve a schema will do it through a hierarchy of caches. There will be an in-memory process local cache that it will be looked at first. If the schema is not found there, the next step would be looking at the host local cache on the local file system. And after that, going to the Maven proxy that you probably have in your organization. The next step would be a CDN, an external CDN where for the Maven repository. And after that, the central repository. This way, the reference resolution cost is minimized. There are two resolver implementations I have created referenced on this page. One based on Maven Ether, and that uses the mechanism that Maven itself uses. And the other one based on Eclipse Jersey, JXRS client. You can use either one based on what works best for your use case. I mentioned previously that schema references make Avro schemas feasible in protocol headers. Let's go over how we can use Avro in the HTTP protocol to improve the type information of the request and response content. In the HTTP protocol, the content type header provides the type information of the content. And as shown here, it is comprised of a media type along with some key value parameters. For Avro binary encoding, the media type is application Avro. But that on its own does not provide much type information about the content. However, we can use a parameter to add the Avro schema to the content type header. As shown in this slide, we can use a parameter named AVSC. You can see how this makes the type information more complete and definitely more valuable. Now, let's see how our type information can play an important role in the HTTP content negotiation. In example number 1, we have a client asking for version 0.3 of a particular schema via the HTTP accept header. This allows the server to respond to the client with the exact version of the model requested by the client, even if the server supports newer version. You can see here the importance of compatible schema evolutions. This wouldn't be possible or easily implementable without compatible schema evolution. In the second example, the client requests an arbitrary projection or a subschema, and the server responds accordingly. In this example, the projection is a name field of a demo record. All this can be supported transparently for binary, JSON, or CSV media types. You can see how one could build pretty flexible RESTful services with Apache Avro. In this slide, you can see an example where we use the accept header to query the latest version of a model in JSON format. We do that by not specifying in the accept header the AVSC content type parameter. The response content type, which you can see highlighted, will contain the media type with the Avro schema of the latest version that the server will support. Here are the server-side implementation stubs in Java with the JXRS framework annotations. I copied and pasted them from a demo application that I have on GitHub. Um, Here you can see the content types that we can use. Application Avro for binary encoding, text CSV for CSV, application JSON for JSON encoding, application Avro X plus JSON for an optimized JSON encoding. With serializer and deserializers available for these encodings, it is trivial to implement flexible endpoints that will get back to the client in various formats, various versions, and various projections without writing any custom code. Now let's go one step further. Um, we have an example here or on this slide where we have four entities defined served by four REST endpoints. And these four entities reference each other. When you want maximum flexibility on how a client can get the data from these resources, for example, when different clients will want to query different combination of these resources joined to each other, and the number of combinations gets large, one option you should consider is using a SQL engine. I say that because when you go ahead and implement your requirements, it will feel like implementing a SQL engine anyways. So it might help if you start with one. One of the options you have is Apache call side, where with a small amount of integration work, you can plug in and adapt your Avro resource data as call side tables, and then translate the query result set into an Avro collection array and serve it via an HTTP REST endpoint. I have implemented this integration and will go over some examples in the next slides. For more information on this integration, see the URL on top of this slide. On this slide, you can see a screenshot of a SQL query in action. We are doing a GET request to a /query REST resource. We are providing the SQL query with a HTTP query parameter. You can see this highlighted on this slide. You can see the query response in JSON format. You can also see highlighted the response content type header, which contains the Avro schema of the response result set. In this case, it's a record with a single field. The name of the field is name. It's a simple example. Here is an example of a query where we use the accept header to ask the results in CSV format. The response, as you can see, is in CSV format. The response headers will have the content type containing the Avro schema, but the content type this time will be text CSV. You can also see a response warning header highlighted in red telling us that we are accessing a deprecated field. The deprecation warning header contains the deprecation message declared in our schema. In this case, the description field for the planet entity is deprecated. This is a way for the server to communicate to the client that the client is accessing a deprecated field, and the client should be then be modified to uh, stop using that field and potentially use an alternative. We have seen so far how Avro can be used to implement REST resources and quite flexible REST resources. And since Apache Avro is an awesome data definition and serialization framework, it fits really well for your application configuration too. Here you can see a configuration object schema on the left. It's just an example, um, and how it can be used in a Kubernetes configuration map on the right side of the slide. Kubernetes configuration map is a standard way of providing configuration to an application. Your configuration models will be defined in schema projects, and you will benefit from the same compatible evolution, quality validations, etc. It is nice to have schemas for your configurations. It's way better than having property files or anything else that doesn't have a schema. Um, Schemas can have documentation, so you can know what to put in a configuration value and etc. There is a lot of advantages to having an Avro schema to the configuration. And it can be this can be enhanced further if we look into using QLang and other technologies together with Avro. Uh, let's see on the next slide how we can use our configuration in a Java application. And as you can see on this slide, it is really simple. Your configuration will be injected by your favorite dependency injection framework. In this example, we reference the config map key with the add config property annotation. And we just use the generated Java configuration class and inject it in our resource when we want to use it. So it is really simple. So this is how one can use Avro. This is how simple it is to use Avro for your application configuration. After seeing how we can use Avro for our configuration, let's look at how we can use it for our operational data, like logs, metrics, profiles, etc. On this slide, you can see an overview of a typical operation data flow setup in a distributed system. As you can see, you can store high-resolution data locally in Avro files and centralize a prioritized and sample subset to a central monitoring system. Avro fits really well both as a storage and as a wire format. The Avro binary encoding is really efficient, and combined with compression, it really is a good way of reducing your I/O overhead. Let's look at how we can use Avro for logs. Here is a screenshot showing the log record Avro schema documentation. This schema is used by the logback backend to persist the application logs into Avro files. The implementation of this logback backend you can find at the URL reference at the top of this slide. Um, in the schema definition, you can see here the usual fields and their types for a log record, like level, timestamp, log message, etc. On top of getting a structure for your logs, Avro binary encoding and compression can reduce your log sizes significantly compared to using JSON or text. Sorry. Here is a screenshot of getting the application logs via an Avro REST endpoint in JSON format. You can see how useful it is to have a JSON encoding available for humans and efficient binary available for machines. And it's also, you can see the advantage of using Avro for storing logs, and then it is very easy to expose it via a REST endpoint. Next operational case for Avro is application metrics. In this screenshot, you can see the metrics metadata Avro model generated documentation. For metrics recording and storing, I use the SPF4J library, which uses Avro for storing the metrics. The SPF4J library uses thread local counters to keep the observer effect at a minimum. While Avro's compact binary representation contributes by reducing the I/O overhead. Here are a few screenshots of application metrics served via Avro REST endpoints. On the left side, you can see the Avro schema of a measurement. In the middle, you can see the measurement data in JSON formats, in this case, a histogram. On the right side, you can see a memory utilization metric exported to CSV and graphed in a spreadsheet. You can see in this example how a CSV encoder comes in handy by making it very easy to export your data to CSV and then load it into your favorite spreadsheet application and then process it further. Next, you can use Avro to model and persist your application profiles. In this slide, you can see the Avro doc for the stack sample element object produced by the stack sampling profiler from the SPF4J library. I use continuous profiling in my project, and as such, my applications produce profile data continuously. This way, I always have data available to investigate performance regressions. Apache Avro's compact representation helps here reducing the profiling overhead. Here are some screenshots of the Avro serialized profile data retrieved via an Avro REST endpoint in JSON format on the left side, and the same data rendered with the D3 flame graph component on the right side. So you can clearly see the advantages that we get with Avro here. We can easily store the profile data and we can easily retrieve it via a REST endpoint and then upload it. The previously shown examples have been produced with a live demo that is running on GKS at the URLs listed on this slide. The source code for this demo is also available on GitHub at the URL reference on this slide as well. As we have seen so far, Avro fits really well everywhere you need to persist or transfer data between processes, and it can be an important building block in the foundation of your distributed systems. Thank you for attending this talk, and I hope you found this presentation useful. If you want to contact me for any feedback and question about this presentation, I included here my email and my GitHub contact information. If you have any questions to the Apache Avro community, join our channel on Slack. Again, thank you and looking forward for your feedback. Thank you.